Okay, in this problem we have a homogeneous rectangular plate which is released from rest with its upper surface being horizontal. We're asked to assume that the point O is smooth, and to take this information to determine the maximum angular velocity of the plate as it rotates about its pin support. So since we're looking at an angular velocity after a change in position, we know this is a problem that's going to involve the work energy equation. And so what I'm going to want to start to do is draw a free body diagram for the system at an arbitrary orientation angle. So if I do that, I know I'm going to have reaction forces at point O, which I can call OX and OY. And I'll have a weight, which will act at the center of mass, and I can call this just simply W. Now if I do this, I can note that the points OX and OY, or forces I should say, OX and OY, are not going to contribute non-conservative work because point O doesn't move, and the weight will be accounted for in the potential energy. So with that being said, I can say that T1 plus V1 plus the non-conservative work moving from state 1 to state 2 is going to equal T2 plus V2. And furthermore, I can say that the non-conservative work done moving from state 1 to state 2 will be 0. In addition, I know the plate is released from rest, so the initial kinetic energy is going to be 0. And if you'd like, I can go ahead and set the datum here in Vg equals 0, and we can use that to help us find the rest of the terms. So how am I going to do that? Well, I can note that first of all, if I put my datum through point O, the potential energy at state 1 is going to be given by minus mg, the weight of the plate, times the location of the center of mass below point O, which in this case is given by d over 2. In terms of T2, I know the object's going to be in pure rotation about point O, so I can write this as 1/2 times I about O times omega 2 quantity squared. I don't necessarily know I about O, so I can rewrite this using the parallel axis theorem as 1/2 times I about G plus m times the distance between points O and G, quantity squared, times omega 2 quantity squared. I can then note that for a rectangular plate, I about G is given by, in this case, 1/12 times the mass of the plate times its height squared plus its width squared. And I'm going to add to that m times the distance from O to G squared. And we can find that distance, it's the hypotenuse of a triangle here, and we can note that in this case the vertical side of the triangle is d over 2, this side is 1.5d, and so we can find here dog by simply using the fact that we know dog quantity squared has got to equal d over 2 quantity squared plus, in this case, 3d over 2 quantity squared. Once I have those terms, I'll have only one unknown in T2, which is omega 2. I can then find the potential energy at the second state. If we want to find the point where the velocity is maximum, what I can note here is that's going to be the point where dog, that is directly below, or I should say the center of mass G is directly below O, which gives me a distance of dog. So I'll have here minus mg times dog. If we take these three unknowns and plug them back into the work energy equation, we'll end up with a result here for the angular speed at state 2, omega 2, which is exactly what we were asked for in this problem statement. From there on out, it's a relatively straightforward numerical exercise, and one I know you're well equipped to handle. So I'll simply wish you the best of luck. Take care, everyone.